In this video, we're going to go through the right triangle definitions of trigonometric functions, and then we're going to do a few examples of evaluating trigonometric functions. So let's begin with our right triangle. So here we have our right triangle, and this is going to be theta, or our angle of interest. Across from theta is our opposite side. Touching theta and our right angle is our adjacent side, which leaves our last side opposite of our right angle as a hypotenuse. Sine is the opposite side divided by the hypotenuse. Cosine is the adjacent divided by the hypotenuse, and tangent is the opposite over the adjacent. Cosecant, secant, and cotangent are the reciprocals of sine, cosine, and tangent, which gives us the hypotenuse over the adjacent, the hypotenuse over the opposite for our cosecant, for secant, the hypotenuse over adjacent, and for the cotangent, the adjacent over our opposite. To help us remember, because it can kind of be a lot, we have SohCahToa. So the S is for sine, which would be opposite over hypotenuse. The C is for cosine, which is adjacent over hypotenuse. And our T is for tangent, which is our opposite over adjacent. So SohCahToa helps us to remember the order of our ratios. Let's try one and put it into practice. So in this first example, we're going to find the exact values of the 6 trig functions of theta. So again, remember, we want the exact values, which means we don't want to use a calculator. We're going to leave them in fraction form. So here we have our theta. So we're going to label our sides. So here we have our hypotenuse, which is what we don't know. We have our opposite side and our adjacent side. Now, because we don't know what our hypotenuse is, we're going to use the Pythagorean theorem to find our value for the hypotenuse. So we're going to plug in our 4 and our 3. So we have 4 squared plus 3 squared equals x squared, which gives us 25 equals x squared. Taking the square root of both sides, we're going to use x equals 5. We're not going to worry about the negative 5 because we're talking about the distance, and so we can't use the negative there. So now that we have that value, we have the value of all 3 sides of our right triangle, which means we're ready to find our 6 trig functions. So to find our sine, we're going to have the opposite over the adjacent, 4 over 3, the opposite over the hypotenuse, which is 4 over 5. And then our cosecant is that reciprocal, so 5 over 4. Our cosine is the adjacent over the hypotenuse, so we'll have 3 over 5, and the secant is that reciprocal, which is going to be 5 over 3. Our tangent is the opposite over the adjacent, which is 4 over 3, and the cotangent is going to be the reciprocal of that, which is 3 over 4. And so that's our answer for that particular portion, is we have now found the exact values of the 6 trig functions of theta. Now let's look at another example with a special right triangle. So our next 2 examples are going to involve a 45 degree triangle and then a 30, 60, 90 degree triangle. So we're going to begin by finding the exact values of the sine of 45 degrees, the cosine of 45 degrees, and the tangent of 45 degrees. Again, we're looking for the exact values. So we're going to have fractions. So we're going to find our theta, or our angle of interest, 45. So that tells us that our opposite side is going to be a 1, our adjacent side is going to be a 1, and our hypotenuse is going to be that radical 2. Let's find the sine of 45 first. So again, its opposite was a 1, and its hypotenuse was a radical 2. But we can't leave a radical in the denominator, so we're going to need to rationalize it by multiplying the denominator and the numerator by radical 2. Doing that is going to give us the sine of 45 equals radical 2 over 2. And that is going to be our exact answer, or value, for the sine of 45 degrees. If we're looking at the cosine of 45 degrees, remember that that's going to be our adjacent over our hypotenuse. So we'll have our adjacent, which is 1, and our hypotenuse, which is radical 2. Again, you can't leave a radical in the denominator, so we'll multiply both the numerator and the denominator by radical 2, which is going to give us that the sine of 45 degrees is radical 2 over 2. So we've just found the exact value of the cosine of 45. To find the exact value of the tangent of 45, we're going to need to take the opposite, which is 1, over the adjacent, which is 1. And so we'll have a 1 over 1, which is the tangent of 45 degrees, equals 1. So that's the exact answer of the tangent of 45 degrees. Now, if we use the equilateral triangle shown here to find the exact values of the sine of 60 degrees, the cosine of 60 degrees, the sine of 30 degrees, and the cosine of 30 degrees, we're going to first need to start off by picking what we're going to do. So we'll just kind of go in order. So we're going to find the sine of 60 degrees first, which means our angle of interest is going to be this 60 degrees right here. So because that's the case, this is going to be our opposite, this is going to be our adjacent, and of course this is going to be our hypotenuse. So to find our sine of 60 degrees, we'll have our opposite over our hypotenuse, and there's nothing to reduce there, and there's not a radical in the denominator, and so that's going to be the exact answer for the sine of 60 degrees. Now if we're looking for the cosine of 60 degrees, we're going to need our adjacent over our hypotenuse, and again, can't reduce that, and there's no radical in the denominator, so this is going to give us the exact value of the cosine of 60 degrees. Next, we want to find the sine of 30 degrees though, and because we're finding the sine of 30 degrees, that changes our angle of interest. So although our hypotenuse will stay the same, because we're looking at our angle measure now of 30 degrees, that changes our opposite to the 1 and our adjacent to the radical 3. So here, the sine of 30 degrees is going to be the opposite, which in this case is a 1, and our adjacent, or excuse me, our hypotenuse of 2. And there's nothing to simplify, and there's no radical in the denominator, so we're done. So the exact value of the sine of 30 is 1/2. Now, if we're going to look for the cosine of 60 degrees, we're going to need to take our adjacent, or radical 3, over our hypotenuse of 2, and there's nothing to reduce, and there's no radical in the denominator, and so this is going to be our solution for our exact value. Oh my goodness, that's not, that should say 30. We just did that for 30. There we go. And so that's our exact value for the cosine of 30 degrees. Now, something that might come in handy later is if you kind of check and see, like, what's 60 plus 30? 90, right? So kind of take a look at what happens to these values, right? They kind of switch, but that can come in handy later for some other things, or you might remember that from another class as well. More specifically, if we talk about the sines, cosines, tangents of special angles, which is what we just kind of found, we found that the sine of 30 degrees is 1/2, which is exactly what we had calculated. And so here we see for each of our special angles what the sine, cosine, and tangent is for each value, and it will always be that value. Now, there are cofunctions of complementary angles, and which is what we just kind of just saw. So the complement of 90 degrees is going to equal the same thing as whatever the cosine of theta was, which is what we just saw in our last example. Remember that we talked about that if we have the sine of, so we have our 30 and our 60, then that's going to equal, because 30 plus 60 is 90, right? Then that's supposed to equal my cosine of whatever my angle is. Well, the angle I was looking at was the 30, and the cosine of 30 is 3/2. And so we can see that right there. So that's what that is saying. And so it goes through it, these different cofunctions of complementary angles for sine, cosine, tangent, cotangent, secant, and cosecant. So kind of see how those go together. Those come in really handy. So you either want to try and memorize these or write them down into a useful place. We'll be able to use them throughout your problem solving.